Hi everybody. Today we're going to be going over quality of service concepts. So we're going to talk about our network transmission quality, our traffic characteristics, queuing algorithms, QoS models, and implementation techniques. Those are some of the things we're going to learn in this module. So there's a great video on the purpose of QoS. Please make sure that you watch that video because it really gives a good detailed explanation. But basically what we're trying to do is we're trying to prioritize traffic. And for example, when traffic volume is greater than what can be transported across the network, devices will queue or hold the packets in memory until the resources become available to transmit them. Queuing the packets is going to cause delay because new packets can't be transmitted until the previous packets have been processed. If the number of packets to be queued continues to increase, the memory within the device is going to fill up and then the packets are going to get dropped. So one QoS technique that can help with this problem is to classify data into multiple queues as shown here. Network congestion causes delay. An interface experiences congestion when it's presented with more traffic than it can handle. Network congestion points are ideal candidates for QoS mechanisms. The typical congestion points are aggregation, speed, mismatch, and LAN to WAN. Fixed delay is the amount of time a specific process takes, such as how long it takes to place a bit on the transmission media. Variable delay takes an unspecified amount of time and is affected by factors such as how much traffic is being processed. And jitter is the variation of delay of received packets. For packet loss, so without the QoS mechanisms, we could lose some data. So when a router receives real-time protocol digital audio stream for VoIP, or voice over IP, it compensates for the jitter that's encountered by using a playout delay buffer. The playout delay buffer will buffer these packets and then plays them out in a steady stream so that there isn't any jitter. For losses as small as one packet, the digital signal processor, or the DSP, will interpolate what it thinks the audio should be, and no problem is audible to the user. When jitter exceeds what the DSP can do to make up for the missing packets, that's when your audio problems are heard. And some of the different characteristics of traffic. Back in the early days, all we had to deal with was data traffic. There wasn't any unpredictable bandwidth need. We didn't have video and audio streaming constantly. And as you can see, according to Cisco Visual Networking Index, 70% of the traffic in 2017 was video. By 2022, video is going to represent 82% of the traffic. And I'm sure that just in the past 3 weeks alone, that has increased exponentially because everybody's classes are going online now. So the type of demands that voice, video, and data traffic place on the network are all very different. Voice packets have to receive a higher priority than other types of traffic because it's very sensitive to delays and dropped packets. Cisco products use the RTP port range 16384 and 32767 to prioritize voice traffic. Jitter should be no more than 30 milliseconds and packet loss no more than 1%. Voice traffic will require at least 30K of bandwidth, or kilobits per second of bandwidth. So video traffic is unpredictable, inconsistent, and bursty. It's less resilient to loss because it would be pretty weird if you were watching a Netflix video and all of a sudden an entire frame was missing, right? So the number and the size of the packets varies, and it's based on the content of the video. UDP ports 554 are used for real-time streaming protocol, RSTP, and that should be given priority over other less delay-sensitive network traffic. Latency should be no more than 400 milliseconds. Jitter should be no more than 50 milliseconds. And video packet loss should be no more than 1%. Video traffic requires at least 384 kilobits per second of bandwidth. Traffic delay can be smooth or bursty. Network control traffic is usually smooth and predictable. Some TCP applications can consume a large portion of network capacity because they're doing that three-way handshake, which adds some latency. FTP could consume as much bandwidth as it can get when you download a large file like a movie or a game. If you're doing it through FTP, it's just going to suck up all the bandwidth that's available. And some of the things that you need to think about is, does the data come from an interactive application? Is the data mission critical? So those are some of the things that we want to think about when we're setting up our prioritization for our quality of experience. So the way we deal with this is through queuing algorithms, and there's a bunch of different methods. There's a video on QoS algorithms that explains FIFO and WFQ and class-based weighted fair queuing and low latency queuing. And it's all just a matter of, how do we all stand in line and get our help. Queuing is a congestion management tool that can buffer and prioritize and, if required, reorder the packets before being transmitted to the destination. For FIFO, the first in, first out queuing buffers, it has no concept of priorities or classes of traffic or anything else. Whoever gets in line first moves through first. There's only one queue, all the packets are treated equally, and the packets are sent out of an interface in the order in which they arrive. First in, first out. With weighted fair queuing, it's going to apply some priority or weights to identify traffic, classifies it into conversations or flows, and then determine how much bandwidth each flow is allowed to relative to the other flows. WFQ classifies traffic into different flows based on the source and destination IP addresses, MAC addresses, port numbers, protocol, and types of service values. WFQ is not supported when tunneling and encryption because these features modify the packet content information required by WFQ for classification. A class can be assigned characteristics in class-based weighted fair queuing, such as bandwidth, weight, maximum packet limit. The bandwidth assigned to a class is the guaranteed bandwidth delivered during congestion. So packets belonging to a class are subject to the bandwidth and the queue limits, which is the maximum number of packets allowed to accumulate in the queue, and that characterizes the class. Once the limit is reached, tail drops are going to discard any packets that arrives at the end of the queue that has completely used up its packet holding resources. This is the default queuing response to congestion. Tail drop treats all traffic equally, and it does not differentiate between classes of service. If you've already used up all your bandwidth, by the time you get to the end, it might get dropped. Then we have low latency queuing, and it brings strict priority queuing to CBWFQ. So strict priority queuing allows delay-sensitive packets such as voice to be sent over before packets in other queues. LLQ allows delay-sensitive packets like voice to be sent first before the packets in the other queues, giving delay-sensitive packets preferential treatment over all the other traffic. Cisco recommends that only voice traffic be directed to the priority queue. Then we have different models for quality of service. And there's a good video that explains the best effort, int-serve, and diff-serve. Once again, please watch the video. So int-serve, so 3 different models. We've got best effort, int-serve, and diff-serve. Int-serve provides the highest guarantee of quality of service. It's very resource intensive and therefore it's not very easily scalable. Diff-serve is less resource intensive and more scalable. Int-serve and diff-serves are sometimes co-deployed in networks quality of service implementations. So you can use both of them. The best effort model treats all network packets in the same way. So an emergency voice message is treated the same way that a digital photograph attached to an email is treated. And that may not be the best thing. For int-serve, we're using resource reservation and admission control mechanisms as building blocks to establish and maintain our quality of service. It uses a connection-oriented approach. Each individual communication must explicitly specify its traffic descriptor and requested resources to the network. The edge router performs admission control to ensure that available resources are sufficient on the network. Int-serve also uses the resource reservation protocol, RSVP, to signal the QoS needs of an application's traffic along devices in the end-to-end path through the network. If network devices along the path can reserve the necessary bandwidth, then the originating application can begin transmitting. If the requested reservation fails along the path, the originating application does not send any data. So it's either going to work or it's not going to send it. For diff-serve, it's a simple and scalable mechanism for classifying our traffic. It's not an end-to-end quality of service strategy because it can't enforce end-to-end guarantees. Hosts will forward the traffic to a router which classifies the flows into aggregates or classes and then provides the appropriate quality of service policy for these classes. It enforces and applies the quality of service mechanisms on a hop-by-hop basis, so router by router, uniformly applying global meaning to each traffic class to provide both flexibility and scalability. As the packets traverse the network, each of the network devices identifies the packet class and services the packet according to the class. It is possible to choose many different levels of service with diff-serve. And some of our quality of service implementation techniques. There's a video talking about some of the implementation tools and traffic marking. Some of the ways that we can prevent drops in sensitive applications because we want to avoid packet loss, of course. We can increase the link capacity to ease or prevent congestion. We can guarantee enough bandwidth and increase buffer space to accommodate bursts of traffic from fragile flows. WFQ, CBWFQ, and LLQ can guarantee bandwidth and provide prioritized forwarding to drop sensitive applications. We can drop lower priority packets before congestion occurs. Cisco iOS QoS provides queuing mechanisms such as weighted random early detection, or WRED, that start dropping lower priority packets before we get any congestion occurring. So a couple of different categories of quality of service tools. We've got our classification and our marking tools, congestion avoidance tools, and congestion management tools. So here, this shows the sequence of QoS tools when applied to packet flows. The ingress packets are classified and their respective IP header is marked. To avoid congestion, packets that are are then allocated resources based on defined policies. The packets are then queued and forwarded out the egress interface based on their defined QoS shaping and policy and policing policy. Methods of classifying traffic. Basically, it flows at layer 2 and layer 3, and that includes using interfaces, ACLs, and class maps. Traffic can also be classified at layers 4 through 7 using network-based application recognition, or NBAR. How traffic is marked usually depends on the technology. The decision of whether to mark the traffic at layers 2 or 3, or both, is not trivial, and it should be made after consideration of some of these points. So layer 2 markings of the frames can be performed for non-IP traffic. Layer 2 marking of the frames is the only QoS option available for switches that are not IP aware. And layer 3 marking will carry the QoS information from end to end. So the 802.1q is the IEEE standard that supports VLAN tagging at layer 2 on Ethernet networks. Do you guys remember that? So when 802.1q is implemented, 2 fields are inserted into the Ethernet frame following the source MAC address field. 3 bits are going to mean that a layer 2 Ethernet frame can be marked with one of 8 levels of priorities, values from 1 through 7. And both IPv4 and IPv6 support an 8-bit field for marking. The type of service, TOS field in IPv4, and the traffic class field in IPv6. So we've got type of service and traffic class. The type of service and traffic class carry the packet marking, an assigned marking as assigned by the QoS classification tools. And here's a whole bunch of different RFCs that specify the precedence and how to manage that. Our DSCP values organized into 3 categories. We've got best effort, expedited forwarded, or assured forwarded, depending upon how important the data is. And our values, so our assured forwarding values are shown here, and we're using our first 3 significant bits to designate the class. Class 4 is the best queue, and class 1 is the worst queue. So the 4th and 5th significant bits are used to designate the drop preference, and the 6th most significant bit is set to 0. Our class selector bits. So the first 3 significant bits, and they're going to indicate the class. That's going to map directly to the 3 bits of the COS field and the IPP field to maintain compatibility. So traffic has to be classified and marked as close to its source and technically administratively feasible. So that's our trust boundary. These are going to be all of our devices that we're in charge of. Our trusted endpoints. Have the capabilities and intelligence to mark application traffic to the appropriate layer 2 COS or layer 3 DSCP values. Our secure endpoints can have traffic marked at the layer 2 switch, and traffic can also be marked at layer 3 switches and routers. So some congestion avoidance techniques provide preferential treatment for which packets get dropped. Our weighted random early detection, or RED, allows for congestion avoidance on the network interfaces by providing buffer management and by allowing TCP traffic to decrease or throttle back before buffers are exhausted. WRED helps avoid tail drops, and it also maximizes network use and TCP-based application performance. Traffic shaping is going to retain excess packets in a queue and then schedules the excess for later transmission over increments of time. Traffic shaping results in a smooth packet output rate. Shaping is an outbound concept. Packets going out of an interface get queued and can be shaped. In contrast, policing is applied to inbound traffic on an interface. So policing is applied to the inbound traffic on the interface. It's implemented by service providers to enforce a CIR, or a contracted customer information rate. Something to note, though, is that the service provider may also allow bursting over the CIR if the service provider's network isn't currently experiencing congestion. So you may get a higher CIR than you were expecting, which is nice. So some of the policies: you have to consider the full path from source to destination. You want to enable queuing at every device in the path between source and destination. We want to classify and mark our traffic as close to the source as possible, and we can shape and police traffic flows as close to their sources as possible. The end. We went over QoS, video and voice and live video transmissions, and you have a perfect opportunity throughout this process of us going remote now to rate my QoS over the bandwidth limitations that I have here. We've got voice can tolerate a little bit of latency and jitter without too many noticeable effects. Video is way more demanding because of the size of the packets it sends. Queuing is a congestion management tool that can buffer, prioritize, and reorder the packets if necessary. And there are a number of different queuing techniques: FIFO, WFQ, CBWFQ, and LLQ. And different models for implementing our QoS is best effort model, integrated services, INTSERV, and differentiated services, DISSERV. 3 categories of tools: classification and marking tools, congestion avoidance tools, and congestion management tools. And classification determines the class of traffic to which packet frames belong. We can classify our traffic flows at layer 2 and 3. We can also classify it at layers 4 through 7 using network-based application recognition. And congestion avoidance tools help monitor our network traffic loads in an effort to anticipate and avoid congestion at common network and inter-network bottlenecks before congestion becomes a problem. And Cisco iOS has weighted random early detection as a possible congestion avoidance solution.